So good morning, everyone. Thank you for joining this security session. I'm Xavier Bignalet again, the Secure Product Manager, the Product Manager for the Secure Product Group at Microchip. So we had a few hints this morning on the topic, and I'll dive right into it. So the whole philosophy of the security model of LoRa is based on shared key. So what does it mean? That there is a master root key that has a different name that has to be the same on both the node and the backend. And the whole challenge here is how do we distribute that key in a secure fashion across the millions of nodes of LoRa devices. So let's start to how we get a key today. Johan and Winky showed a picture I'm going to reuse here. Literally, it could start from an Excel spreadsheet that is being sent over email, being accessed and visible by many people, down to literally receiving your keys into an envelope and on a paper. That's the worst thing you can possibly do in terms of security practices. Again, remember the concept. If I have the key, I am you. So if I have the key of the device, I can impersonate the transaction of the device. We need to alleviate that. We need to remove that issue. So we look at how the LoRa Alliance has built the security model. Nicolas Sorin was talking about it. You have different type of keys. Here I'm giving the model of the LoRa 1.1 security model that has an app key, a network key, and you use both of them to derive the respective session keys, right? So on the device side, those keys are accessible because they are going to be, they are very often in the flash of the microcontroller. Flash is very accessible. If you want to know how and how this is being done and how this is being accessed, come and see me at the booth and I'll show you a few websites that are actually proposing services to extract not only the keys but the complete X file of your microcontroller. Again, if I have the key, you remember that concept. The vulnerability doesn't stop there, right? Because we have that same key again on the end node and the backend. So on the backend, what happens? The keys are between the network server and the application server. So those are Linux environments, and Linux is software. Software has bugs. It is normal, right? And software is alive. Those bugs is what will be exploited by attackers. The way that works, generally, when you have a bug, there's a patch. The patch is disclosed. That's what the attacker will look into to see if there is a door through the software. It's much easier to get into software than into hardware, right? So we've got vulnerability on the node, on the back end. And then we have another challenge, the change of ownership. Let's say I want to use TTI servers, and tomorrow I want to use another provider. How is the key being transferred? How is that authority being moved from one server to the other? Right? That's where problems start to happen again, because the origin of that key is not controlled. It's not very well proven, backed up. We have a problem of trust between server A and server B and how we transfer that key. Then, furthermore, the issue goes down to the end nodes, because if we don't have the trust at the roots, that problem of trust is going to be broken all the way down to the edge node. So that's I was going to give you a story. That's really where the fun begins. I have a little daughter here. I was alone at home for the week. My wife was traveling, and I came into her bedroom. It was very silent, so that means there's a problem, a very big problem, right? 4 years old like this. Coming to the bedroom, and that was her face, because it was a mess, and she knew it. Well, in LoRa, that's kind of what happened. We have a pretty messy challenge in the supply chain. So to illustrate that, if you think about the business ecosystem of LoRa, you have a product owner. It's you guys. You develop the end product. You will contract production site, contract manufacturer to manufacture your devices at scale. And then we have an application server where the keys need to go. Well, there you go. Now we have that shared key that needs to be the same from the product owner and the server, or the production side and the server. All those things being shared today. We're back to the envelope model, where literally keys are copied, pasted, sent over non-necessarily secure links. There is no trust established between each of the, there is no trust that can be verified down to a root among all the different providers. The complexity adds up because now with LoRa 1.1, we introduce the concept of network key. It's a second root key. And we double up the problem. So now same problem with the network server in terms of logistics, right? Because those keys need to be the same at the network server as well as the site of the product owner and the site of production. So the example here is, imagine if we take a use case, the connected cow, that's one cow of one herd for that one farmer. Now you have multiple cows in that herd, right? You have multiple farmers across the industry. Take multiple use case within the agricultural segment and go across segment, medical, smart building, and everything that Johan and Winke was presenting there. And you ended up with multiple production, multiple product owners, multiple servers, network, application from different providers, same providers. And that's when my daughter, that's what that picture really made the face of my daughter really in the previous slide. What do we do about that? So that's where we've been super excited of combining a silicon with a service into a single purchase. That's what you get. You'll get a silicon, which is really a secure key storage that's pre-provisioned. So you can look at that secure element as a memory with a lot of security features that I'll detail later on. And it has different set of policies to allow the slot to do something, right? A verification, a signing operation. So all those policies have been preset, and the keys are already loaded inside the device. All of that uses Microchip's secure provisioning service. What that means is Microchip is equipped with a backend and a programming center equipped with hardware secure modules, and that's where the secrets will live. We use that flow to generate the secrets within the secure boundary of the secure element. That doesn't stop. That is what our business is every single day. So we ship those configured and provisioned devices. It could be custom part number, generic. Well, things that are starting to get really cool here is we bundle, when you buy the device from us, it's bundled with 1 year service of TTI joint server services. That's what you get. You buy the device, inside the price is bundled 1 year service. You don't have to pay TTN for that first year. And the last bullet point is very interesting. You know, I talked about the change of ownership. Both the secure element and the joint server are equipped with the capability of rekeying the system. It's a command that will be sent by the joint server to change the keys. So we talk about key rotation really here. If we look a little bit more into the details, here I have the scheme for LoRa 1.0.x that has one root key to generate 2 session keys. The other value here is it's compatible with LoRa 1.0.x and LoRa 1.1. With the same device, it will be able to support both standards. And on the back end, the joint server services, which are managed HSM from TTI here, is also obviously compatible with both services. Now what we have here, we have a secure boundary, which is the secure element at the node, and you have a secure boundary around the keys in the backend, which is the joint server of TTI. That's how the keys are protected. Now, how are the keys going there, right? We've seen keys moving all over the place in one of the slides. That's not quite what happens, actually. We don't want the key to move all over the place. And another correction I need to make, the keys are not injected. They are generated by the device. Johan mentioned the complexity, showed the paper and all those papers going all over the place to get the keys. So what we created with TTN came to us a few months ago and said, hey, okay, this is my problem. This is the problem we see in the LoRa industry that slows down the adoption. How can we solve that with the secure element? You got your storage, that's fine. I've got my storage in my backend, and that's fine. Now, how do we push the keys there? So after a lot of definition, a lot of engineering work, this is how the flow looks like. You, the customer, would go to Microchip and buy that generic part number. I'll say it only once. It's called the AT-ECC608A, MAHTN. Once you place your order, we validate the payment. When the payment has been validated, what happens is we create a manifest, which is really a JSON file. and we start manufacturing the chips. Then what you have created your Microchip account where you'll download this file, this manifest, and at the same time, we ship the secure element. Now, here's the important thing. Instead of sending envelope all over the place, obviously you can't send a full-blown HSM, right? It's the size of a server. You can't ship that. You can't put that on a PC. That's not possible. The analogy of it is actually the secure element. That's your secure boundary. Now you end up with a little chip. It's a UDFN 8-pin. And that is the vehicle for the keys to move securely all across the globe. That is how you want to distribute keys securely globally with that type of secure element. Once everything is in the hand of the customer, the file and the secure element, there's 2 more steps. The customer, you need to upload that file, that manifest, on the joint server of TTI. So now, the chain of trust is not completely established yet. We're missing something. That is where the whole value of the system kicks in. TTI has established a claiming service of the identity, which is the key, that is securely stored in the secure element. You can make the analogy of the SIM card for the telco, right? Where you have your SIM card in your phone, and when you go to your telco, spin up your cloud accounts, the telco, you activate a function by the telco that will claim the identity that are in the SIM card, right? And then things can start to happen. They can start to charge you. You can start to place phone calls. This very similar analogy. And last, what you've established there, it's secure, trusted. You have a chain of trust based on symmetric keys. But that is also managed, right? And the management comes from the TTI joint server services. What have we done at the edge node here in terms of best security practices for key handling? There are 3 big concepts that we believe in is isolate keys from as many things as you can. Those things are users or, well, myself, my mom, my daughter. The kids that go to college, if you remember the DDoS attack in 2016, I think it was in October, if I'm not mistaken, they found out he was a 19-year-old student that wanted to prove himself to the community. Well, bad things happened to him, I can tell you that. So the community of unethical hacker has a very wide type of profile, which means when a technology becomes successful and visible, like LoRaWAN is becoming today, that will become a target. So users need to be isolated as much as possible from handling keys. And users, to attack the keys, they will try to look into firmware and software holes, right? Like I said, those 2 things are living entities. They are bugs. It's normal. We are human beings developing that code. We will make the mistake. We are the weakest link of the security model, of every security models. So okay, to isolate that too. And the last piece is, of course, the manufacturing. The manufacturing phase, what do you have in manufacturing? You have operators and equipments. What's running those equipments? Well, guess what? It's probably a Linux system, right? The proof here, there was something published by Bloomberg a few months ago, so we're back late 2018, where there's a little chip that was discovered in one of the blades used in the server of Apple and Amazon. Both companies verified the facts. So what that means is there have been some unexpected, unwanted chip being placed at manufacturing for some of the most sensitive hardware in the world, really. That lives in data centers. So it's not a unicorn. Vulnerability during manufacturing phase are real. The last piece that's very important in terms of practice to handle keys, we want those crypto primitives to be in the same boundary as where the keys are, right? If you separate the crypto primitive from where the keys are, the keys will likely have to move or be called at some point. That is another backdoor. You do not want to do that. So what is that secure element for those who don't know? It's a companion device to a microcontroller. That is that secure boundary. That's where it's kind of a vault here for the keys are protected. And where how the keys being placed there, they're not actually being placed there. They're being generated after a set of commands that are acknowledged, that have been verified all the way up to the root key. And the devices are generated inside the secure boundary of the secure element based on that command. They're not injected. If you are injected, that means the key, someone had access to that key physically. We don't want that. We eliminate that in the process. And last, how does the microcontroller talk to the secure element? We have something called crypto-auth-lib that has a hardware abstraction layers embedded. And that's how you talk I2C between the microcontroller and the secure element. The way it works in a very simple way, it sends a random challenge, and the secure element uses the key to provide a response back to the micro. That is validated based on the random challenge. And we have a yes or no to continue the connectivity, to establish the connectivity here. And of course, nowhere in the whole process of manufacturing and during the lifetime of the device on the field, the keys will be exposed, extracted, or touched. Never. What do we have inside that chip? We have, if you have to remember two things, we have anti-tampering protection and side channel attack protections. If you want to demystify side attack channel protection, to simplify that, try to use the very basic principle of electronics. You have really four variables in electronics. You get current, voltage, time, which is frequency, temperature. Some of the attack will consist, some of the side channel attacks will consist in making those variables fluctuating in a very special sequence to put the transistor into unsteady state, right, to start leaking information. And that's how key leakage starts to happen. Different types of attacks are listed here. I won't go into the details, that becomes a much longer discussion. So now how do we back up our statement of this is a secure device? So what do we do? If you remember the star rating of energy saving and car safety and all that stuff, those things are being rated by third parties. So that's what we've done in security. It's a good security practice to have. You contract a third party to test your system, to test your facts, the value of your device. So the rule of thumb is, the third party we've used, they're an expert in common criteria. They know everything that needs to be known about SIM card, smart card, payments, PCI Express, and all that stuff. So they use the hacking techniques, and we give them our files. We give them as much as they want to ask us. And the rule of thumb says they have about 3 man-months to extract the key from the device. And this is evaluated with a scale. So what I'm trying, the conception I'm trying to break is security is a mystic thing. It's a unicorn. It's obscure. No, it's not. For the past few decades, what happened is something called, again, common criteria that has a very well-established standard of security test practices. Among that standard, there is a scale that's called EAL that rates from 0 to 7. Scale 7, you're up to the military grade. Scale 1, you have the bare minimum encryption. That standard defines everything you can think of in security, down to how you manage your own project, how the people are being badged to get into the building. Some of our highest-end devices, the TPM that Microchip also manufacture, is common criteria certified. But here we're talking about one specific portion of the standard that touches the secure key storage. That section, that's its own rating. It's called Joint Interpretation Library. And that rating goes from 1 to 31. And if you get anywhere between 1 and 31, that means the key has been extracted with a certain attack that the lab is using, with one known attack that the lab has been using. Well, lucky us, after that time period, the 6 to 8 has been rated GIL high. What it means is we didn't have a number, because it would have been bad, right? We had the best rating on the quality of our key storage that the standards is recognizing. So you could assimilate that to some of the highest EAL rating as part of the full spec, if you want to know. So that's how we back up our statement of secure device. So I'm going to summarize everything. I know if Johan is somewhere in the room, so he's supposed to come on stage. And we'll have a discussion on what have we achieved with TTI here. It's been many things, and we'll kind of play ping pong in that conclusion. The first thing we tried to address was ease of use. You've seen their intro. There is a hurdle. There's cost associated to it. So within the secure element, it's pretty fine to address the authentication to the network, the rekeying, secure boot over-the-air updates. Or if you want to talk about rekeying, that's a huge topic, I think, for the tech.
Yeah, so, yeah, thank you. So rekeying is where you repersonalize the device, and the device gets a new set of root keys. So that means that Microchip ships the device with root keys in there. So that's a network key and an application key. Those are LoRaWAN 1.1 root keys, but they can also be used for LoRaWAN 1.0 LoRaWAN stacks. But if you want to change those keys, there is a procedure that's called rekeying. And rekeying is a mechanism that works on the application layer that sends a nonce, which is a number used once, to the end device over the application layer, over the existing application session. And there it triggers a rekeying procedure. And that generates 2 new root keys. These root keys are not exchanged. So it's not that you, is this one working as well? Is it working? Yeah. It's not that you create or that you send a new pair of root keys over the LoRaWAN session, because that would be insecure. But you send a nonce, and the device uses that nonce to generate a new pair of root keys. But we also need to know that in the cloud. So we have a rekeying server that can migrate from one joint server to another joint server. But the old joint server does not play a role in here. So what happens is, as a device owner, you want to rekey the device. You have a session with the device. You send a nonce. The rekeying server, you go to the rekeying server, you get a message, you send that message, which contains the nonce, to the end device. And in that rekeying server, you also configure which new joint server you want to use. And then the new root keys are sent to that new joint server. So you can migrate from one joint server to another joint server without the old joint server playing a role here. So we have 1 year of TTI joint server included in every secure element that you buy. From then, you can extend that contract if you want to stay on the TTI joint server, or you can migrate to a different joint server, whatever you want. And if you do that, you get new root keys. So what we have in our joint server becomes invalid.
Okay. We think that's where the vision came in from TTI, right? Adding a service on top of the silicon. That's how. I'm going back to the phone example. When you buy a phone, well, you need a service to work, right? And this is what we've tried to achieve with the vision of TTI. The next point is related to good security practices, at least in the back end, right? So both TTI and Microchip are using actually similar hardware. We both have hardware secure module. That's what, I mean, you're from the IT world, I'm from the embedded world. Those are good IT practices. We have some of the cloud providers here, the experts, and do encourage you to talk to them. Microsoft, I know, is here. AWS is also here. They do use HSM in their data centers, right? It's not a new practice. What we've done here in TTI and Microchip, we've continued to use those are basic common practices in security. I don't know if you explain a little bit on it.
Yeah. So that's, I mean, the security of the whole depends on the secure handling of the keys and of the process on Microchip side and our side. And the thing is that we don't know your root keys. The root keys are they are not exchanged. So as Xavier also mentioned before, it's not that Microchip sends us a set of root keys that they put in their devices, or that we set a set of root keys to Microchip to put in the devices, because then we would be exchanging root keys. We don't do that. So we have really come up with a scheme to the key ceremony to exchange a master key from where we derive the root keys that end up in the devices. And this way, because LoRaWAN is symmetric, we have to have the same root keys in the secure element and in the joint server, but we derive the same keys from a secret key that is stored in an HSM.
The next one is a simplified logistic. I mean, we've seen the flow. Basically, you buy the device, you get a file, you upload the file into TTI joint services, claim it, you're done. That's it. One of the last points is the robust security at the edge. Now, I think you got the point with all the GIL high-rated secure elements. Gives you quite a lot of confidence on that. And the last bullet points I'll make here, and then we'll show you how you get started on all that good stuff, is the flexibility and the scalability for you to be able to make business with the LoRa technology in a secure fashion. That's where I think the whole difference is. It's network server agnostic. It's application server agnostic. You can argue it's almost joint server agnostic, right? Because you want the proliferation of that tech. It's microcontroller agnostic because of the usage of the library. It is LoRaWAN stack agnostic. And then we're back to, I don't know if you want to do a few comments. I might throw another one that I'm passionate about, the fact that you have no roaming across the globe.
Yeah.
That is a massive difference against the telco business model. Once you move a device from a country to another with a SIM card, I guarantee you know that you will be charged. So a lot of us are coming from abroad. You wait your bill at the end of the trip. With TTN, that doesn't exist. I don't know if you want to toss a few things.
Yeah, so we have 1 year of service included in the price. That means that there is no additional charge to use the secure element. So you can use this secure solution without additional charges on the public community network, on a private network powered by the Things Industries, or any other LoRaWAN network that implements the backend interfaces. We don't charge other networks to work with our joint server.
So I wrote a bullet point here, audits and end device activity and reporting. What is the benefit of that to the customer?
Sorry?
The auditing and device activity?
Yeah, yeah. So in the joint server, we audit, we log everything that happens with the end device. If the end device sends a join request, according to the LoRaWAN backend interfaces, if the network, the gateway, so the join request is received by a gateway forwards it to a network, and if that network follows the backend interfaces, it will look up the join server to handle the join procedure. And at that point, we start logging the activity. So we see, we log, we make it visible for our users to see where the join requests come from. And it also gives you insight in device activity on the device activation level. But also, that gives you a lot of insight in seeing where we actually send the session keys to for device activation. Yeah.
So now, how do you get started here? So you get that little board, it's a socketed board, where you get the samples, you get all the pricing information for low volumes. You put the sample into that socketed board. That goes to, it is compatible with our SAM R34. It's the system in package that was launched last year by our wireless group here. They will present, I think, tomorrow. It's using the LoRaWAN stack from Microchip. A second solution is a discrete approach using the SAM L21 with the code that ARM has actually developed using ARM Embedded OS and the LoRaWAN stack from ARM. So both of them are actually available on our page today. Now, how does the whole onboarding work? You open the account from Microchip, you buy the device on our store, and the specific part number for TTN. Once we acknowledge the payment, we give you the, where's my laser here? That's where you download the file from our portal. You get the JSON file, it's a public set of information. We don't care if you see it, and that's where we're showing it today. So it logs all the devices that have been purchased as part of your purchase order, right? And then we pray the demo goes.
And then we have the device claiming. So currently, we don't have a very fancy user interface for this. So we have to use CLI. But this is V3 already, V3 stack. So this is the file. This is the JSON file. As Xavier said, there's no secrets in here. This is just a public manifest with a signature. So we know that the file comes from Microchip. So you cannot randomly start claiming serial numbers that you didn't buy, because then the serial number doesn't match. So the next step is where we provision the devices. So we have a CLI. This will be available in the console where you upload the file. But for now, in V3 CLI, you have a command to provision. You say the provisioner is Microchip. This is the file, the JSON file. And you load it into this application. So you do this, you have access to the joint server to do the provisioning. Then you create it. So we provision it is the first step, and the second step is to create those devices that are provisioned. So that is being done now. So now these devices are being created on the network. Here you see some public information that's actually in that manifest, like serial numbers and the manufacturer information, also when it was provisioned by Microchip. And now they are in the device registry. So the devices are now in your account, and you can list your devices. So you can say devices list, and then your application ID. And here are the devices provisioned with the serial number. So that's the serial number of your device, but also a def EUI and a join EUI. And this join EUI points to the TTI join server. So if this device sends a join request, it will go to our join server. It will send the session keys to the network server and application server that you chose to use. And that can be anyone.
Thank you, Johan. Supposed to have a picture of the booth here. So if you have any questions, we're out of time. Microchip has a booth there. I'll be there for the remaining of the event with all the experts there. Come and ask us questions. I want to thank you, ARM, for developing this code, TTN for the whole partnership, all the engineering team that spent a lot of time working on that. And thank you for your attention.